we've covered the idea of logarithms and their limits and their derivatives, but what we haven't done is discuss them in terms of integration. So if we go and we say, okay, well, the derivative of the natural log is 1 over x, and the derivative of the natural log of a differentiable function is 1 over the differentiable function times its derivative by the chain rule, then we can represent these in sort of their antiderivative or integral form by saying that the antiderivative of 1 over x is natural log of x plus c, and the antiderivative of 1 over a differentiable function, with that du, so you'll have that sort of u prime situation there, is natural log of that differentiable function plus c. So it's important that you don't forget about those absolute values. So notice that these don't have absolute values. They could. We've discussed that. But when you take the antiderivative, the general form of an antiderivative involves an absolute value, and of course you always have your arbitrary constant. Never forget that. Now, one thing we're not ready for yet is how we would take the antiderivative of the natural log. Now, the answer to it is x times natural log of x minus x plus an arbitrary constant, and that's a fairly easy derivative to calculate, to verify that this is an antiderivative for that function. But we don't have the techniques for integration yet to get from here to here. So just a little bit of a teaser. Anyway, so let's put this fact to use here. The first one is we have 12 over x dx. So what we want to do is we just say, okay, that's 12 times the antiderivative of 1 over x dx, which is 12 times the natural log of absolute value of x plus c. You could also have rewritten this as like that. So see if you can maybe come up with a general rule relating this constant to that power. It's kind of an interesting piece. The next one is 2 over x minus 4 dx. Now, we have something when it is 1 over x directly, but we don't have it when it's x minus 4. So what we need to do is we need to leverage u substitution. By letting u equals x minus 4, and du at that point just becomes dx, because the derivative of this is just 1, so 1 dx. Then we can use that substitution to say, okay, this is 2 over u du, which is 1 over u du, which is 2 natural log of u plus c, which is 2 natural log of x minus 4 plus c, or x minus 4 squared plus c. So either one of those is fine. Don't forget to go back to x. Once you've got to u, don't forget to go back to your original x. And finally, we have tangent of x dx, which doesn't look like any of this, but what we found out is a lot of the trigonometric integrations involve natural logs. So what we can do is we can say, okay, that's generally speaking, when dealing with trigonometric functions and integrals, if you're having issues, always revert back to their sort of base functions of sine and cosine. That will tend to help you. A lot of times it helps with kind of reframing this. And what you find is I've got something over something dx. Okay, so there's some tricks here for trigonometric or for logarithmic integration. And the key is you identify something in a denominator and you try to see if you can find its derivative in a numerator. what does that mean? Okay, well, in this case, I'm going to let u equal cosine of x. So then the derivative of u is, okay, that's negative sine of x dx. So then negative du is sine of x dx. Okay, so I had something in the denominator. Oh, I can find it. Okay, so the derivative of this, I can kind of absorb it in the numerator. So that tells me that this becomes negative 1 over u du, right? So that negative du, this gets absorbed into that. Cosine becomes u. So now I have negative 1 over u du, which is negative 1 over u du, which is negative natural log of u plus c, which is negative natural log of cosine of x plus c. But remember, the negative can be brought up to, so this is perfectly fine, but what is common in this case is we instead write that as natural log of cosine of x to the negative 1, which is 1 over cosine of x, which is secant of x. So natural log of secant of x. This is generally the way you'll see this. When you see this in integration tables, you'll see that the integral, or the antiderivative rather, of tangent of x is the natural log of secant. But note that that's the same thing as this.